Welcome back. In this video, we're going to look at examples of using the ratio test for series. Let's get to it. All right, so here's our first example. We want to determine if the series converges or diverges. And so for this series, we have the sum from n equals 1 to infinity of n divided by 2 to the power of n. All right, now in general, the ratio test is going to be very helpful for determining the convergence or divergence of a series that includes either a factorial or an exponential part. And so here's how the ratio test works. For an infinite series where we have the sum of a sequence a sub n, if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to some limit L that is less than 1, then our series converges absolutely. If the limit as n approaches infinity of the absolute value of that ratio is equal to some limit L that is greater than 1 or it's equal to infinity, then our series diverges. And then finally, if the limit as n approaches infinity of the absolute value of that ratio is equal to 1, then the test is inconclusive. The ratio test does not tell us if that series converges or diverges, and so we will need to use another test. Okay, and so for a series, if we want to use the ratio test, we need to identify a sub n and write out a sub n plus 1, and then evaluate this limit. And depending on the value of that limit, we can conclude that our series either converges absolutely, that it diverges, or that the test is inconclusive. Okay, so if we go back to our example, in this case, a sub n is just going to be equal to this sequence. So we'll have n divided by 2 to the power of n. And then a sub n plus 1 is going to be equal to that same expression, but we're going to replace each n with n plus 1. So we'll have n plus 1 divided by 2 to the power of n plus 1. Okay, and so now we have a sub n and a sub n plus 1. And so if we want to use the ratio test, we will take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, and that is going to be equal to the limit as n approaches infinity of the absolute value of this expression divided by this expression. Now, instead of writing out a complex fraction of this fraction divided by this fraction, instead remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. And so what we'll have is a sub n plus 1, which is n plus 1 divided by 2 to the power of n plus 1, divided by a sub n, which is the same as multiplying by the reciprocal of a sub n. So we'll flip the numerator and denominator and have 2 to the power of n divided by n. And that is the limit that we need to solve. All right, now whenever you have an exponential part within your limit, you should split up that power, and that will help you to simplify your limit. Right, so 2 to the power of n plus 1 can be split up to be 2 to the power of n times 2 to the first power, right? So this would be equal to the limit as n approaches infinity of the absolute value of n plus 1 times 2 to the power of n divided by 2 to the power of n times 2 times n. All right, 2 to the power of n times 2 would be the same as 2 to the power of n plus 1. When you have like bases and you multiply them, their exponents get added together, and so 2 to the power of n times 2 would be 2 to the power of n plus 1. All right, so we just split that up, and now we can see that 2 to the power of n is in the numerator and denominator, and so they cancel out. All right, and so now our limit will look like this. We have the limit as n approaches infinity of n plus 1 divided by 2n. Now at this point, we don't need absolute value bars anymore. In fact, we could have removed them earlier, since this expression has no way to become negative, because our values of n are from 1 to infinity. They're all positive values, and we're just adding 1 and multiplying 2. And so no matter what value of n we use, this is always going to be positive. And so we will remove the absolute value bars and just have n plus 1 divided by 2n. All right, and so now we just have a limit as n approaches infinity of a rational expression with an algebraic numerator and denominator. And so what we can do to evaluate this limit is look at the highest power of n in the numerator and denominator, and depending on whether those powers are equal or one is greater than the other, we will be able to take a shortcut to the answer for this limit. All right, so in the numerator, we have n to the first power, so that's the highest power of n in the numerator, and in the denominator we have 2n, where n is raised to a first power. So in the numerator and denominator, we have the highest power of n to be 1, and so since those powers are equal, this limit as n approaches infinity will be equal to the ratio of the coefficients from those two terms. So we'll have the coefficient of this n, which is 1, divided by the coefficient of this n, which is 2. So this limit will be equal to 1/2. All right, and now 1/2 is less than 1, which means that from the ratio test, we can conclude that this series converges absolutely. All right, and so we can say that our series converges absolutely. That is the final answer for this example. Since the limit of the ratio between a sub n plus 1 and a sub n is less than 1, we know for a fact that our series converges absolutely. Let's look at another example. All right, so here's our next example. Once again, we want to determine if this series converges or diverges, and this time our series is the sum from n equals 1 to infinity of -1 to the power of n plus 1 divided by n factorial. Now, as I said earlier, whenever you see a factorial within your series, it's going to be a good idea to try and use the ratio test. The ratio test is very good at dealing with factorials if you know how to simplify a factorial. And so you're going to see that in this example. So if we're going to use the ratio test, we need to identify a sub n. In this case, that is -1 to the power of n plus 1 divided by n factorial. And then we also need to write out a sub n plus 1. So we're going to have this same expression, which came from our series, but we're going to replace n with n plus 1. So this will be equal to -1 to the power of n plus 1 plus 1, but 1 plus 1 is 2, so this power is just n plus 2. So we'll have n plus 2, and that is divided by n plus 1 factorial. Now it's important to remember to add these parentheses around n plus 1, because if you didn't do that, you just have n plus 1 factorial, which is a different expression. Instead of having n plus 1 factorial, you have n plus 1 factorial. And 1 factorial is just 1, which completely changes this denominator, and so you don't want to make that mistake. Remember those parentheses. Okay? And so now we have a sub n plus 1 and a sub n. So now for the ratio test, we can look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, and so if we write that out, we will have the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Now, once again, we have two rational expressions or two fractions, and so instead of writing a complex fraction of one fraction divided by the other, it's going to be easier for us to write the first one times the reciprocal of the one we're dividing by, right? So we have a sub n plus 1 divided by a sub n, so we'll just have a sub n plus 1 times the reciprocal of a sub n. So we'll have -1 to the power of n plus 2 divided by n plus 1 factorial, and we're going to multiply that by the reciprocal of a sub n. So we need to flip the numerator and denominator. And so we'll have n factorial divided by -1 to the power of n plus 1. All right, and so that's our limit that we need to evaluate. And so in order to find what it's equal to, we need to do some simplifying. Now, the first thing that I see we can do is completely eliminate these two -1s to the power of n plus 2 and n plus 1. The reason why we can eliminate those is because we have these absolute value bars. The absolute value bars are going to ensure that this expression is always positive. And -1 to the power of n plus 2 or -1 to the power of n plus 1 can only be one of two values. It'll either be +1 or -1. So if we're taking the absolute value of those parts, they're both always going to be 1, and so we can just completely eliminate them from the expression. They're not going to have an effect on the rest of our limit. All right, and then n factorial and n plus 1 factorial are always going to be positive values, and so now we don't need these absolute value bars anymore. This will be equal to the limit as n approaches infinity of n factorial divided by n plus 1 factorial. Okay, now at this point, we need to be able to reduce this limit further by eliminating these factorials. But how are we going to do that? We need to be able to manipulate a factorial in order to evaluate this limit. And so recall, if you have a factorial, let's say we have 4 factorial, that's equal to 4 times 3 times 2 times 1. But we could also write it like this. We could say that 4 factorial is equal to 4 times 3 factorial, right? And that would be the same answer because 3 factorial is 3 times 2 times 1. So if we have n plus 1 factorial, we could rewrite that to be n plus 1 times n factorial, right? We have our value that is in the factorial times a factorial where we have a value that is 1 less than that value, okay? So we have n plus 1 factorial is equal to n plus 1 times n, which is 1 less than that value, and that is where the factorial will now be. Okay, so hopefully you can see what is going on here. We are going to rewrite n plus 1 factorial right down here to be n plus 1 times n factorial, and watch what that allows us to do. This will be equal to the limit as n approaches infinity of n factorial divided by n plus 1 times n factorial. Now we have n factorial in the numerator and denominator, and so those are going to cancel out, and we're just going to be left with the limit as n approaches infinity of 1 divided by n plus 1. All right, so if we go through with that evaluation, this is equal to the limit as n approaches infinity of 1 divided by n plus 1, which now is a fairly simple limit that we can evaluate, right? As n approaches infinity, we have 1 divided by n plus 1, and n is getting bigger and bigger, and we're adding 1 to it. So this whole denominator is approaching infinity, and a fixed value divided by infinity, or 1 divided by infinity, is always going to be equal to 0. The values are going to get smaller and smaller towards 0. And so this limit is equal to 0, which is less than 1, which means that from the ratio test, we can conclude that this series converges absolutely. All right, and so that is going to be our final solution for this example. Our series converges absolutely. All right, and so that is the conclusion that we can make from the ratio test. Because the result of our limit was less than 1, we know for a fact that our series converges absolutely. All right, let's look at another example. Okay, so next up we want to determine if this series converges or diverges. We have the sum from n equals 0 to infinity of 2n factorial divided by n factorial squared. Now this looks insanely complex, but it's actually not as bad as it looks. Right away, when you see a factorial in the numerator and denominator, you can immediately decide to use the ratio test. The ratio test is very good for a series with factorials. And so let's write down a sub n and a sub n plus 1, and then we'll look at how we are going to evaluate the limit for what seems to be a pretty complicated expression. All right, so a sub n is equal to 2n factorial, and that is divided by n factorial squared. All right, now if we replace n with n plus 1, we will have a sub n plus 1. So a sub n plus 1 will be equal to 2 times n plus 1 factorial divided by n plus 1 factorial squared. All right, so we replaced this n with n plus 1, and we replaced this n with n plus 1 as well. All right, now let's simplify this a little bit. Instead of having 2 times n plus 1, let's just multiply this 2 through this quantity. So 2 times n is 2n, and 2 times 1 is 2. So what we really have here is 2n plus 2 factorial. So I'll write that, 2n plus 2, and that is still affected by this factorial. And now let's take a look at our limit for the ratio test. We will take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, so in this case, that will look like this. The limit as n approaches infinity of the absolute value of this fraction divided by this fraction. Now, once again, in order to avoid a very complex fraction, we're just going to multiply by the reciprocal of a sub n. So we're going to have a sub n plus 1 times the reciprocal of a sub n. All right, so we'll have 2n plus 2 factorial divided by n plus 1 factorial squared, and that's going to be multiplied by the reciprocal of a sub n. So if we flip the numerator and denominator, we will have n factorial squared divided by 2n factorial. Okay? And so how are we going to go about simplifying this limit so that we can evaluate it. Because at this point, there's nothing we can do to evaluate this limit as n approaches infinity with these factorials. And so what we want to try to do is eliminate all factorials from this limit. And that seems like a tall order at first, but the first thing that I see that we can do is rewrite the factorials that are being squared. And so let me show you what I mean by that. What we can have is that this is equal to the limit as n approaches infinity of the absolute value of this expression. But by the way, we don't need those absolute value bars because all of our values of n are from 0 to infinity, which are all positive, and the result of a factorial is always going to be positive. And so we don't need those absolute value bars, but we will have 2n plus 2 factorial, but then I'm going to rewrite n factorial squared to just be n factorial times n factorial, right? This will be multiplied by n factorial multiplied by itself. That is the same as n factorial squared. Now in the denominator, I'm going to do the same thing for n plus 1 factorial squared. We're just going to have n plus 1 factorial times itself. And that will be multiplied by 2n factorial. All right, so there's a lot going on here, but now we can sort of start to see what we can do to maybe simplify this limit. Remember what we did in the previous example. We said that n plus 1 factorial is equal to n plus 1 times n factorial. We take that value and then multiply it by 1 less than that value factorial. Okay, so we can replace each of these n plus 1 factorials in the denominator with this expression, n plus 1 times n factorial, and those n factorials are going to cancel out with these two in the numerator. So that's good, but what about 2n plus 2 factorial and 2n factorial? Well, we can do the same type of manipulation to our factorial here. We can say that 2n plus 2 factorial will be equal to 2n plus 2 times 2n plus 1 factorial, right? We have that value from the factorial, and then we multiply it by 1 less than that value and put the factorial there, right? 2n plus 2, 1 less than that will be 2n plus 1. And if we do that again for this factorial, then this will be equal to 2n plus 2 times 2n plus 1 times 2n factorial, right? To rewrite this factorial, we'll have 2n plus 1 times 1 less than that value, which is just 2n, because 2n plus 1 minus 1 will be 2n, and then we put the factorial there. And so we can rewrite 2n plus 2 factorial right here to be this expression right here. And this 2n factorial will be in the numerator and will cancel out with this one in the denominator. Now I actually wrote that a little bit incorrectly. This should be 2n factorial with parentheses around it. All right, and so now you can see that those two will cancel out if this is in the numerator. And so if we rewrite this limit by replacing these two factorial expressions with this expression and replacing this with this expression, then we will be able to make a lot of cancellations and have a limit that we can evaluate. So if I clean up my work here, this limit will be equal to the limit as n approaches infinity of 2n plus 2 times 2n plus 1 times 2n factorial times n factorial times n factorial divided by n plus 1 times n factorial times n plus 1 times n factorial times 2n factorial. And so this 2n factorial cancels out with this 2n factorial, this n factorial cancels out with this one, and this n factorial cancels out with that n factorial. And now we have eliminated all factorials from our limit. What we're left with is the limit as n approaches infinity of 2n plus 2 times 2n plus 1 divided by n plus 1 times n plus 1. Right? Those are the parts that we have left in our limit. Everything else canceled out. And just note that in the denominator, we have n plus 1 times n plus 1. That's actually the same as n plus 1 squared, right? Since we have two of those factors, we could just rewrite that to be one of them squared. So we'll have n plus 1 squared. Okay? And so now we have a limit that does not have any factorials in it that we should be able to evaluate. And so if I clean up my work here again, we can evaluate this limit by first expanding the denominator and foiling these two factors or multiplying them together. So if we do that, this will be equal to the limit as n approaches infinity of 2n times 2n, that's going to be 4n squared. Then we have 2n times 1, so we have plus 2n. Then we'll have 2 times 2n, which is 4n. And then finally we have 2 times 1, which is positive 2, so we have plus 2. And 2n plus 4n is 6n. So I'm just going to rewrite this to be 6n plus 2. And so then our numerator is complete. And then for the denominator, we want to square n plus 1. So I'm going to use a little trick to do that quickly. We'll square the first term, so n squared is n squared. Then we'll multiply the two terms together and multiply them by 2. So n times 1 is n, times 2 is 2n, so we have plus 2n. And then our last term will be 1 squared, which is 1. All right, and so now our limit is in its fully expanded form, and so we can take a look at each of the terms in the numerator and denominator, because what we have here is a rational expression with an algebraic numerator and denominator that we can easily evaluate as n approaches infinity by looking at the highest powers of n in the numerator and denominator. And in this case, the highest power of n in the numerator is n squared, and the highest power in the denominator is also n squared. And so since those powers are equal, this limit as n approaches infinity will be equal to the ratio of the coefficients for those terms. So the coefficient of this n squared in the numerator is 4, so we'll have 4 divided by the coefficient of this n squared, which is 1. So our limit will be equal to 4 divided by 1, which is equal to 4. And 4 is greater than 1, which means from the ratio test that our series diverges. It does not converge to any value. All right, so that is going to be our final answer. Our series diverges. And that is the conclusion that we can make based on the value of our limit for the ratio test. All right, so here's our next example. We want to determine if the series converges or diverges. In this case, our series is the sum from n equals 1 to infinity of n to the power of n divided by n factorial. All right, so once again, we have another factorial as well as an exponential part, and so this series is a good candidate for using the ratio test. So let's identify a sub n and a sub n plus 1. A sub n will be equal to n to the power of n divided by n factorial, and a sub n plus 1 will be equal to this same expression, but n is going to be replaced with n plus 1. So all three of these n's need to change to be n plus 1. So we'll have n plus 1 quantity to the power of n plus 1 divided by n plus 1 factorial. All right, so for the ratio test, we will have the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, and so that will look like this. We'll have the limit as n approaches infinity of the absolute value of this fraction divided by this fraction. And so once again, instead of writing out a complicated fraction, we're just going to write a sub n plus 1 times the reciprocal of a sub n. And that is the same as dividing by that fraction. All right, so we'll have n plus 1 to the power of n plus 1 divided by n plus 1 factorial, and that will be multiplied by the reciprocal of a sub n. And so if we flip the numerator and denominator, we'll have n factorial divided by n to the power of n. All right, and so now the first thing we want to do is eliminate that factorial. We do not want that within our limit so that we can evaluate it. And so this is our third example where we have had n plus 1 factorial. So hopefully you are familiar with how to manipulate that at this point. We can rewrite n plus 1 factorial to be n plus 1 times n factorial. So our limit will be equal to the limit as n approaches infinity of the absolute value of n plus 1 to the power of n plus 1 times n factorial divided by n plus 1 times n factorial times n to the power of n. All right, we just rewrote n plus 1 factorial to be n plus 1 times n factorial. Okay, so now that n factorial in the numerator and denominator will cancel out, and so we are left with this limit. We have the limit as n approaches infinity. And I don't think we need these absolute value bars because all these values of n are going to be from 1 to infinity. So nothing is going to make this expression negative. So we're just going to have n plus 1 to the power of n plus 1 divided by n plus 1 times n to the power of n. All right, now we can actually simplify this a little bit more yet. We can split up this power of n plus 1, and so we would have n plus 1 to the power of n times n plus 1 to the first power. So I'm just going to erase that, and we'll have n plus 1 to the first power. And now you can see that we have an n plus 1 quantity in the numerator and denominator that will cancel each other out. And so this will be equal to the limit as n approaches infinity of n plus 1 to the power of n divided by n to the power of n. All right, now at this point, it's not initially clear how we can go about evaluating this limit. But do notice that the numerator and denominator are both raised to a power of n, so we can make that power the power of the whole fraction. And so if I clean up my work here, I'll show you what that looks like. We will have that this is equal to the limit as n approaches infinity of n plus 1 divided by n raised to the power of n. All right, since the numerator and denominator were both raised to that power of n, we can just have that whole fraction raised to that power. Okay, now if we were to look at this expression as n approaches infinity, in the numerator here, we would have infinity, because n is approaching infinity plus 1 is still infinity, and that would be divided by n, which is approaching infinity. So we have infinity divided by infinity raised to the power of infinity. So that's no good. We have no idea what this limit is equal to. And so we have to try to manipulate this a little bit more. And so I'm going to split up this fraction. We'll have n divided by this denominator, and then add that to 1 divided by this denominator as separate fractions. So that'll look like this. We'll have the limit as n approaches infinity of n divided by n plus 1 divided by n to the power of n. Right, you can always split up the numerator of a fraction. And so then n divided by n is equal to 1. So I'm just going to rewrite that. We will have 1 plus 1 divided by n, quantity to the power of n. Now, if you watched my videos on L'Hopital's rule, you might recognize this limit that we have right here. We have the limit as n approaches infinity of 1 plus 1 divided by n to the power of n. And as n approaches infinity, 1 divided by n is going to approach 0, because we have 1 divided by infinity, or an increasing value. So we have 1 plus 0, which is 1, raised to the power of n, which is approaching infinity. And so this limit is in the indeterminate form of 1 to the power of infinity. And so in order to get around that, we have to do some manipulation to our limit. And then eventually we will be able to use L'Hopital's rule. All right, and that's going to involve taking a derivative of the numerator and denominator of our limit once we get it in a form where we have a rational expression. All right, and so what can we do to make this limit easier to solve? Well, since we have a power of n, a good way to deal with that power is to introduce the natural log function, because a natural log function, or any logarithm, allows us to move an exponent to the front of an expression. And so here's what we're going to do. We're going to let y be equal to this limit, right? So we have y is equal to the limit as n approaches infinity of 1 plus 1 divided by n to the power of n. And it doesn't matter what variable you choose here. I chose to use y. You could pick x, you could pick z. It doesn't matter. Just pick some variable to set equal to that limit. And then what you're going to do is take the natural log of both sides of this equation. So we'll have the natural log of y is equal to the limit as n approaches infinity of the natural log of 1 plus 1 divided by n to the power of n. Now, when you have the natural log of an expression raised to a power, you are allowed to move that power to the outside of the natural log function. That is one of the properties of logarithms. And so what we will have is that the natural log of y is equal to the limit as n approaches infinity of n times the natural log of 1 plus 1 divided by n. All right, and now if we look at this limit as n approaches infinity, we're actually not quite yet ready to evaluate it, because this n approaches infinity, so this is equal to infinity times the natural log of 1 plus 1 divided by n. And as this n approaches infinity, we have 1 divided by infinity, which is 0. So we have 1 plus 0, and the natural log of 1 is 0. So we have infinity times 0, which is another indeterminate form, but it's not an indeterminate form that we can use L'Hopital's rule for. So we still have to manipulate this limit a little bit more. But thankfully, it's not too difficult to make that manipulation. All we have to do is multiply by a form of 1 divided by n, and that is going to remove this n from the numerator, and we're going to have 1 divided by n in the denominator, right? N times 1 divided by n is just 1. So we will have the natural log of y is equal to the limit as n approaches infinity of the natural log of 1 plus 1 divided by n divided by 1 divided by n. And now we have a limit that is compatible with L'Hopital's rule, because look at what form this limit is in. As n approaches infinity, we have the natural log of 1 plus 1 divided by n, and 1 divided by infinity is 0. So we have the natural log of 1 plus 0, or the natural log of 1, which is equal to 0. So we have 0 in the numerator, and then in the denominator, we have 1 divided by n, which also approaches 0. So we have 0 divided by 0, which is an indeterminate form that is compatible with L'Hopital's rule. So we can take the derivative of the numerator and denominator of our limit in order to simplify it and then try to evaluate it again. All right, so if I clean up my work here, we can now use L'Hopital's rule on our limit here. So let's take the derivative of the numerator and denominator separately. And if we do that, we will have that the natural log of y is equal to the limit as n approaches infinity of the derivative of the natural log of 1 plus 1 divided by n. Now the derivative of the natural log function is 1 divided by the inside function times the derivative of the inside function. So we have 1 divided by 1 plus 1 divided by n times the derivative of 1 plus 1 divided by n. Now the derivative of 1 is 0, but the derivative of 1 divided by n, remember that that is the same as n to the negative first power. So the derivative of that, by using the power rule, we multiply the exponent down to have negative n, and then we subtract 1 from the exponent. So our derivative is negative n to the negative second power. And then if we take the derivative of the denominator, we have 1 divided by n again, which is still n to the negative first power. And so the derivative will also be negative n to the negative second power. All right, so we have that same expression in the numerator and denominator after using L'Hopital's rule. So we can actually cancel that out. Negative n to the power of negative 2 is going to be eliminated from the numerator and denominator, and we will be left with the following. We'll have the natural log of y is equal to the limit as n approaches infinity of 1 divided by 1 plus 1 divided by n. All right, and so if we take a look at this expression, as n approaches infinity, we have 1 divided by 1 plus 1 divided by n, and so we have 1 divided by infinity, which is 0. So the natural log of y is equal to 1 divided by 1 plus 0, which is just 1 divided by 1, which is 1. So if I erase that, this is equal to 1. But remember, that is not the result of our original limit. Remember that we set that limit equal to y, and so we need to solve for y in order to find what our ratio test limit is equal to. And so to solve for y, we're going to make both sides of the equation the power of e. And so if we do that, we will have this equation. We'll have e to the power of the natural log of y is equal to e to the power of 1. And e and the natural log are inverse functions, and so they cancel each other out. And so we're just left with y is equal to e. And so I'm going to write that over here. We'll have y is equal to e. And so e is what our limit for the ratio test is equal to. All right, and so e we know is approximately equal to 2.7, which means that e is greater than 1. And so since that result of our limit is greater than 1, that means that from the ratio test, we can conclude that this series diverges. All right, so our final conclusion is that our series diverges. Okay, that is what we can conclude since the value of our limit was greater than 1. Okay, let's look at one more example for this video. All right, so here's our final example. We want to determine if this series converges or diverges. And this time we have this series, the sum from n equals 1 to infinity of 1 divided by 3 times n plus 2. All right, now this series doesn't have any exponential parts or any factorials, so I'm not necessarily convinced that the ratio test is the right test to use for this series, but let's try it anyway. Let's see what happens. And so in this case, a sub n is equal to 1 divided by 3 times n plus 2, and a sub n plus 1 will be equal to 1 divided by 3 times n plus 1 plus 2, but 1 plus 2 is 3, so we're just going to have n plus 3 in the denominator. So we'll have n plus 3. Okay, so now let's take a look at our limit for the ratio test. We'll take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. All right, and so that's going to look like this. We'll have the limit as n approaches infinity of the absolute value of a sub n plus 1, which is 1 divided by 3 times n plus 3, and that's going to be multiplied by the reciprocal of a sub n. That is the same as dividing by that fraction. So we'll flip the numerator and denominator and have 3 times n plus 2 divided by 1. All right, so now if we simplify, this will be equal to the limit as n approaches infinity of the absolute value of 3 times n plus 2. That's going to be 3n plus 6, right? 3 times n is 3n, 3 times 2 is 6, and that will be divided by 3 times n plus 3. So that will be 3n plus 9. All right, 3 times n is 3n, 3 times 3 is 9. Now at this point, we don't need these absolute value bars. N is always going to be a positive value from 1 to infinity, and so then we're just multiplying them by 3 and adding positive values, and so this expression will always be positive, so we don't need these absolute value bars. Okay, now for this limit, as n approaches infinity, note that we have a rational expression where the numerator and denominator are both algebraic, and so we want to look at the highest power of n in the numerator and denominator. In this case, in the numerator, the highest power of n is n to the first power, and that's the same highest power we have in the denominator. We have n to the first power. So since those powers are equal, this limit as n approaches infinity will be equal to the ratio of the coefficients for those two terms. In this case, we will have 3 divided by 3. And so this limit is equal to 3 divided by 3, which is equal to 1. And when your limit for the ratio test is equal to 1, the test is inconclusive. The ratio test isn't going to tell us anything about our series. And so my suspicions from the beginning were correct. Since this series didn't include any factorials or any exponential parts, it wasn't a good idea to use the ratio test for this series. And so because the ratio test was inconclusive, we now need to use another test in order to determine if this series converges or diverges. So we're kind of going back to square one here. We sort of wasted a little bit of time, but it never hurts to try the ratio test if you're absolutely not sure what test to use. But in this case, we will need to backtrack and use a different test. And so what test can we use for this series? Well, first off, let me just rewrite it a little bit. I'm going to say that this is equal to the sum from n equals 1 to infinity of 1 divided by 3n plus 6. I'm just going to multiply that 3 through this quantity. And this series looks very similar to a p-series, so maybe we can compare it using a comparison test to a p-series, right? We have 1 divided by 3n plus 6. If we remove that 6 and ignore that constant multiple of 3, we could compare this to a p-series of 1 divided by n. In fact, that would be the harmonic series, which is the sum from n equals 1 to infinity of 1 divided by n. And the harmonic series is a divergent series because it's a p-series where p is equal to 1, which means that it diverges. All right, if p is greater than 1, then it would converge, but when p is less than or equal to 1, then it diverges. And of course, p is the power of n. I don't think I mentioned that, but we have 1 divided by n raised to the first power, and so that's what our value of p is. P is equal to 1. All right, so now we have a comparison series that diverges, and so should we use a limit comparison test or a direct comparison test? Well, generally, I find the limit comparison test to be easier when we are comparing to a p-series, and so I'm going to use that. So I'm going to write that down. We are going to use the limit comparison test. All right, and so what we will do is look at the limit as n approaches infinity of the sequence from our original series divided by the sequence from our comparison series. All right, so in this case, that will look like this. We'll have 1 divided by 3n plus 6 divided by 1 divided by n. But this is what we've been trying to avoid this whole video. Instead of having a complicated fraction, we've been multiplying by the reciprocal of the fraction we're dividing by. So let's do that again. Instead of dividing by 1 divided by n, let's multiply this by n divided by 1, the reciprocal of 1 divided by n. All right, so here's what we'll have. We'll have 1 divided by 3n plus 6 times n divided by 1, and that will be equal to the limit as n approaches infinity of n divided by 3n plus 6. Okay, now once again, we have a limit as n approaches infinity of a rational expression where the numerator and denominator are both algebraic. They both have terms with n raised to a power. And so if we look at the highest powers of n in the numerator and denominator, we have n to the first power in the numerator and n to the first power in the denominator. Those are the highest powers of n. And so since they're equal, they're both 1, the value of this limit will be equal to the ratio of those coefficients. So we have 1 for the coefficient of this term divided by 3, which is the coefficient of this term. So this limit as n approaches infinity will be equal to 1 divided by 3, or 1/3. And now for the limit comparison test, as long as this limit, where you have the original sequence divided by the comparison sequence, if that is equal to a finite value, then you can conclude that your original series shares the same convergence or divergence as your comparison series. So since this limit is equal to 1/3, which is a finite value, we can conclude that our series diverges just like our comparison series. So our final answer for this example is that since the sum from n equals 1 to infinity of 1 divided by n diverges, that's our comparison series, then we can conclude that the original series, the sum from n equals 1 to infinity of 1 divided by 3 times n plus 2, must also diverge. All right, that is the final answer for this example. We were able to conclude that our series diverges using the limit comparison test. All right, so remember, if the ratio test fails, don't give up, don't stop, use a different test. You should be able to still conclude if your series converges or diverges by using another test. The ratio test is not going to work for all series, but it will work for the majority of series that include exponential parts and factorials. It's not so good for series like this one that are very similar to a p-series. Okay, so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.